Hey everybody, my name is Dane Fichter. I'm a software developer at Johns Hopkins Applied Physics Lab. Been working on OpenStack for close to 2 years now. I'm here to talk to you guys today about end-to-end security in OpenStack. So in particular, I'm here to talk to you about two block storage encryption features and one feature which performs verification of digital signatures associated with disk images. Why would you want to encrypt things? Well, there are many reasons. Some of them are listed here. Just to say it simply, you just don't want attackers to get to your data. And I think that's all that needs to be said about that slide. Okay, so how does block storage work in OpenStack generally? Well, initially, as the instance is provisioned, the compute host will provision something that we're going to call ephemeral storage, but you can essentially think of it as scratch space for the VM. So when the VM is created, this ephemeral backing file is created, and when the VM instance is deleted, so is the ephemeral backing file. Initially, we also have a concept of volumes in OpenStack. And here, this diagram gives the general layout for how it works. Basically, you have iSCSI magic happening over the network, which transfers the data to and from Cinder, which is your storage host. You've got a local sort of instantiation of the volume, which is mounted onto the VM instance. So how does it work when encryption's in the mix? Basically, we have the addition of this Barbican service, which you see at the bottom there, which may or may not be talking to a KMIP appliance. When we boot our instance, now this extra step of key management is involved. You can see that the compute host is reaching out to Barbican to grab a key for that ephemeral backing file and passing that to de-encrypt. Similarly, when you have a volume being mounted, an encrypted volume being mounted, there's the same action of reaching out to Barbican, grabbing the key, passing it to de-encrypt. And then de-encrypt is basically acting as a sort of persistent filter. So any data that the VM instance is writing to storage, whether it be an ephemeral backing file or an attached volume, is encrypted, and anything that it's being read is being decrypted by de-encrypt. Now we're going to move on to signed images. This is a relatively new feature in OpenStack, so I'm going to kind of take it a little bit more slowly here. So this is how images are booted generally when there's no verification involved. So essentially, starts out, the user uploads their image data with associated metadata, which describes the image properties to Glance. Glance stores the image. When the instance would like when the user would like an instance of this image, they request it from Nova. Nova will then request the image data from Glance. Glance will return the image data along with the associated metadata as properties. Then this is the only verification check that occurs in the normal not signature verification workflow. Nova just simply performs an MD5 verification. Basically, it gets an MD5 hash associated with that Glance image on the initial upload, and then it runs a very cursory MD5 hash against that image, just to make sure that the radio gods haven't flipped a bit on that initial transmission. And then if everything's okay, Nova simply boots the image. So if you have a paranoid mindset when it comes to information security, like I know I do, you can see some problems, some vulnerabilities with this workflow. The first one being during upload, there's always man-in-the-middle potential whenever the user is communicating something to a remote service like Glance. The second is during storage. If someone compromises your storage node, they can compromise your disk image. And a disk image containing malware can become a source of infection across many different virtual machines easily. And lastly, there's, again, man-in-the-middle potential between Glance and Nova. So this led us to the conclusion that image integrity requires cryptographic protection, both from man-in-the-middle attacks that happen between services and user and services, and also as a means of preventing against the image data being corrupted at rest. As you can see behind me, over the last 2 years, there have been multiple CVEs which relate to the integrity of the image as it rests in Glance. So what do we do about this? The answer is signed images. And as you'll see, we also have Barbican in the mix on this feature as well. Essentially, when the image is fetched, there is a certificate UUID, which is also fetched, which allows the compute host to reach out to Barbican to retrieve a certificate. And then using this, the public key associated with certificate, as well as signature metadata, which is appended to the glance image, we perform signature validation. And assuming that everything is OK with the glance image, we go ahead and boot the VM instance. So this is a stronger cryptographic protection of the image data that we go ahead and check before we boot the image. So now that we've talked about all these features, let's see a quick demo where we use them all in tandem to help you get a feel for how the workflow of this goes down. If you guys attended the volume encryption seminar yesterday, some of this will be pretty similar. Okay, so we're going to start by creating ephemeral storage. What we're doing here is we're basically creating a volume group, if you want to use Linux parlance for it, and we're mounting it on a loopback device. There's no particular reason why it's a loopback device. You could do it anywhere where there's persistent storage. Yep, so that's what we're doing initially. And as we can see, that volume group is successfully created right now. There we go. Okay. Once we've done that, we need to boot our compute host, but not before we've configured it. So these are just some configuration options that have to happen in order to enable signature verification and to tell the hypervisor where to look, essentially, for that ephemeral backing file, as well as to enable communication with the key manager. All of this is covered in the Etherpad for this talk, the Etherpad's linked at the end, so I won't linger on this too long. The next step is signing the disk image. So we're going to start out by downloading a Suros image. We're going to use OpenSSL's digest command. As you can see, we're specifying SHA-256 hash. We're using our PEM private key. And yes, there's that Suros image again. And once we've saved the signature bytes, we're going to move on to the next step, which is to upload the certificate. So the certificate contains the public key. We just use the private key associated with that public key to sign the disk image. We're going to use Barbican's secret store command. We need to specify the encoding of our bytes, our certificate bytes, rather, and we need to stream those to the key manager. And once we have accomplished that, we're going to get back this secret href. And the last field in that secret href URL is going to be our cert UUID, which we will give to Glance, along with that Glance image in the next step. So now we're going to upload the image to Glance. We're going to call our image signed Suros. If you take a look at this command line here, you can see that we're streaming the base 64 bytes of the signature as a Glance image property called image signature. We're also giving the hash method again, SHA-256, so that the compute host and the image storage host know what hash method to use to try and verify that signature. And once we perform the upload, we're going to see this response that has all of the associated signature metadata properties listed here. So we're seeing the signature, the cert UID, the hash method, and the key type. And so Glance actually has signature verification enabled as well. So if you upload an image with these properties and you get this response, you know that everything is OK. It's actually, the Glance has actually done the signature verification as well. So once we have our signed image in our image store, the next step is to boot. Something nice that you may notice about this boot command is that it's completely unchanged. So to the end user, this boot procedure looks exactly the same. You've done all this configuration work. If you're an admin, you've gone through the trouble to upload this signed image. But to the end user, it looks exactly the same. They get an extra security check, and they don't even know it. Just as a form of due diligence, I'm going to show you an example of how you would check the compute logs, just to make sure that everything's OK. We're going to grep for the phrase signature verification in the compute host logs. And we can see in our little log message here that it succeeded for the image ID, which is associated with the signed Suros image that we uploaded earlier. And this is where things will start looking familiar if you attended that volume encryption seminar yesterday. We're starting out by creating a volume type. We're going to call it Lux. Next, we're creating an encryption type. We're specifying the cipher. We're going to specify the key size. And finally, we have to specify the class in Nova, which will actually perform the encryption. And once that encryption type is created and has been associated with that volume type, we're going to create that volume. I'm just going to create a small one, 1 gig. And once that's created, we're going to see that we get a volume ID back, which is what we're going to use to attach it. And there's that volume UID. Okay, so now we're going to attach it to our secure instance, which we've booted from a signed image. There's our volume UUID, and we're going to mount it on dev VDB. All right, so now we have our instance running. Let's think about what we've accomplished here. We know bit for bit, we have cryptographic verification that our image is bit for bit the same as it was when we uploaded it. That's a big deal. Second off, all the bytes that are being written to and from the instance, or rather, all the bytes that the instance is writing to storage are encrypted, whether it be in the form of the ephemeral backing file or the attached volume. So that's a +2. Here are all the links for everything I've referenced in this talk, as well as some of the next security features we're pursuing. One of them is a more robust sort of standard X509 validation for the certificates that are being used for image signing. We're also planning on integrating the cursive library into Nova. And of course, there's the Etherpad link for anybody who wants more information or wants to see a more robust sort of procedure than what I've laid out very quickly in this demo here. All right, thanks for listening to this talk, guys.